This is the second video in our video series about static program analysis. In it, we're going to introduce the Tiny Imperative Programming Language, or TIP. We'll first go through TIP's context-free grammar. So first up, we have basic expressions. These are things like integers, or adding to expressions, dividing to expressions, variables. These little vertical bars you see between the symbols just represent ors. So we can sort of read the I expression as integer constants are 0 or 1 or -1 or 2 or -2. Variable identifiers x are things like x or y or z. Expressions e are integer literals or variables or any of these other arithmetic expressions. We'll have a few different statements, assignments, outputting expressions, to statements, if-then-elses, and while loops. Functions are just identifier names, identifiers representing the variable inputs, an optional variable declaration, that's what the question mark is for, a statement, and then a return expression. Records are collections of fields where each field has a specific name. We can create a record with this top line, or we can access a specific field with the name X with the second line here. In TIP, we're going to be able to reference memory on the heap using pointers. So we have an alloc expression that lets you specify an expression to be evaluated, and TIP will take that data and place it in the heap and return a pointer to it. We have ampersand of X. That'll create a pointer to a program variable. *e dereferences a pointer value. We can also assign values through pointers as follows. TIP has functions as first-class values. Functions can be assigned to variables or passed into other functions. We can also have an expression that returns a function, so we'll generalize our grammar to support these kinds of function calls. The first e is an expression that will evaluate to a specific function ID. And now P, or the program as a whole, is just a collection of these functions. There's going to be a special function named main, which initiates sort of the execution of the program. So here are some examples of TIP functions for computing factorials of some numbers. First, we have an iterative version, and we also have a recursive version. Both look pretty standard. Static analyzers need to deal with programs, and in order to simplify the types of programs we deal with, we can do something called normalization, which is to reduce all of the possible programs that we can express in our language to a subset that's more manageable to work with, but still represents the same semantics of our original space of programs. For example, we can normalize programs to always dereference particular variables instead of general expressions. So if we had an expression like that, which is dereferencing this e, we could instead normalize it to something like dereferencing a particular variable. We can also flatten expressions wherever they appear, including function calls or arithmetic expressions. So let's do that here. X equals f of y plus 3 times 5. So instead of this expression here, we can just sort of flatten that into a new temporary. So let's make a new program. So temporary 1 is just y plus 3. And we'll make a new temporary that's f of this first temporary, right? And then as a whole, x is just this second temporary times 5. So we've just flattened our program, but it's still doing the same computation. So far we've been representing programs as text, but something compiler engineers have figured out is a very useful way of representing programs is something called abstract syntax trees, or ASTs. We'll take a look at one right here. So this abstract syntax tree represents the same thing as this other program that we see here. There's this variable n, this variable f. We're setting f equal to a value, we have a while loop, and we have a return statement. But instead of representing all of these constructs as text, we'll put them into a tree formation. And with this representation, it's sort of easier to see the structure of the program as a whole. One other way of representing programs is through control flow graphs. In a control flow graph, or CFG, nodes represent statements of code, and edges between these nodes represent possible program flow between these statements. A CFG always has one entry point and one exit point. For example, this is the control flow graph for an assignment. The entry point is the top circle and the exit is the bottom. We similarly can have control flow graphs for things like outputs, return statements, and variable declarations. To sequence two of these simple statements together, we just put the entry point of one right up against the exit point of the previous one. And so that sort of represents the previous one's control going into the next one. You can also represent constructs like while loops and if statements with these control flow graphs pretty naturally, I think. So for if statements, we'll have an expression that'll sort of branch out into two possible statements being executed because there are two different ways the control can flow. And we can label each branch either true or false. Similarly, for while loops, we'll have an expression with a true branch and a false branch, but the false branch just goes to the exit, and the true branch will end up repeating. So this is the control flow graph for our factorial function. You can see we start by declaring this variable, setting an initial value. The rest of this sort of represents the loop, and we have the true and false conditions, and in the end, we'll just return the value back.